Okay, so in the name of God, the compassionate, the merciful, thank you everyone for coming along. And I'm going to say hello to those who are going to watch this later. Today we have unusually little number of people attending. Hopefully the others will also watch the recording. So this is going to be the last of our 6 sessions on Idris. If I manage to get the admin to oh yeah, it's coming into very good. Yeah. So if I manage to get the admin to agree that I also teach you something next semester or next term. I'm not sure about what is called in University of Bergen. Then we can go further on with the book if you'd like. But for now, this is going to be the last section. Oh, sorry, the last chapter of the book that I am going to teach. Hello, Jan. Tell me.
Hello,
Niels.
hello. Can you hear me?
Right. Oh, it was Jan. Right. Yeah.
Yes.
Hello,
Oh, am I making sound?
Yes.
Yes, perfect, perfect. Sorry about being so late. My network died.
Oh.
I think James should have told you. I sent him a message.
Oh, I didn't get one.
Right.
All right.
Okay, well, fair enough. Now you're here.
Yes. What should I tell you?
You don't need to tell me anything.
All right.
Right. So this chapter is amongst those who have very little TDD attached to them. And therefore I don't think I will show you any Visual Studio, probably a little bit towards the end, but not much. I'll just go through the book. So this chapter is about something that you have experienced a number of times in the language, and it's now going to be your first touch in what that thing is, and that's interfaces. Now, you guys being familiar with the type classes of Haskell, I won't spend a lot of time in teaching you like the basics. So I'll flash through. Now let's go on with the book. So the book starts by reminding you about the fact that you have been using these annotations about the requirements and the types. And so it's trying to say that, there is somewhere that these things were defined. And you have already seen the other, interfaces like functor and monad. And, well, it tries to say that, look, this is something you're familiar with. Don't panic. And then it goes into saying that, well, if you're a Haskeller, then you know that there are similarities, but beware of some of the very little differences. And so the thing is that it's one of the main differences between Haskell type classes and about Idris interfaces is that they are not picky on the number of type parameters and where on which side of the arrow they are, and they can be any types, and you can put because types and values are kind of same citizens, same level citizens in Idris. You can also put constraints on both types and values. And the other thing which is also very interesting is that you can have multiple implementations of hello. Right.
Oh, that's somebody in the background. I'm sorry.
No worries. I just thought that was a question. So the other thing is that it's like multiple implementations of an interface can actually live side by side. You don't need to have a unique one in the scope. So right now, let's take a look at some of the ones that you can most easily go through. You have already seen EQ and ORD. So you have, for example, seen the typing of the equal sign operator, and you know that there is this constraint on the type. And so if you pay close attention, you will see that there is something about inequality, and so you might wonder where that thing is, right, or what it contains. Now the book goes through a series of explorations in order for you to kind of get to see that there is actually a need for something like that to be around, and it essentially is trying to justify its choice of interfaces by saying that, okay, let's say that we have a function called occurrences that looks into a list of values, and it finds as many it finds out how many occurrences of this value of this type there are in this list of that type. And so because it has to go through and make comparisons, at some point it says that, okay, if you do that, then you take the TDD steps, and then when you want to perform this, the compiler stops you and says, oh, wait a moment, you didn't tell me that this type was an equality comparable, right? Now, if you would like to go through this, you do it on your own. I mean, you have seen it, and I have seen you guys, being quite careful about it. That's because you guys know enough about Haskell. So I don't think I need to go through this with you. In case you were wondering what the syntax is for when you require more than one type constraint on a type, this is what you want. So you put them in a pair of round parentheses, comma separated. So that's another thing. And then now, so then the book tries to tell you how or what the syntax is for implementing an interface. So in order for the book to do that, it defines this matter data type, and then it tells you that, come on, what's happened? Okay, if we want to define equality for this data type, then we have to take a look into the types involved in the interface EQ. So you can also look this up in your Idris REPL. You ask it for the documentation of EQ, and you actually get a very nicely printed version of this gray colored thing here, right? So that's that. as you can see, well, a type that is equality comparable is the one that supports two operators. The first of them takes two instances of that type and returns a bool, and so is also the second one, right? Now, right. So this is a naming convention of the book. It's not that you have to call them Thai, for example, like here, but the book, and it's common in the world of Idris that you, when you are doing like interfaces, you give them a name that is suggestive of this being a type. Now, enough of the interfaces. So let's say that you would want to implement this interface for the data type matter that we just defined. Well, it's only that every type constructor of the data type matter is just equal to itself. So that's why you get these three true cases, and anything else is false, right? And then it defines inequality in terms of equality by negating it. Now, so I recommend that you on your own try to go for the TDD of this. And the reason is that you will see unexpected things. So, I mean, it's you would expect this to be much more developed than what you're going to get. So it's good practice that you you do the TDD and you try to come up with explanation for yourself, convince yourself about why things are going that way, right? It's very instructive. Now, so, right, I'm not going to go through that. By the way, one thing that will probably surprise you a bit is that the book's explanation is not what you're going to get, right? So I suggest that you go through the explanation of the book and you try to follow the steps and see what will you get. I think I'm done with this part of it. Right. Now, so one thing which you probably were likely to think on your own is that why did we need to define for the case of matter the inequality when for every type inequality would likely be the negation of the equality, right? Now for that case, for that reason, these two operators have what is called default definitions, which just defines one of them in terms of the other, and what that means is that it suffices that you define just one of them, and the other one would be defined if you leave it out, right? So, for example, it would suffice if for the case of matter, we would only define the cases for equality and leave out the inequality, because Idris can use the default implementation for the inequality and figure out the consequences in that terms. Now, sometimes when you are doing when you're defining one interface, then the type that is going to be the parameter, the type that is going to be the parameter of that interface itself requires to be constrained. So, for example, if you are doing well, this is about the implementation, not the interface itself. So if you are doing like an equality for trees, then you can you make it to right. So you make it to here, and then what you're doing is that you're saying essentially that two empty trees are equal, and if it's going to be otherwise, then well, two trees are equal if the left subtree and the right subtree and the roots are equal. And when you want to do that, there is this part of it which is on the comparison of the element that is in the root, and oops, when you make it to that point, you realize that well, there is a constraint on LM that we have missed. All right. So in the implementation, then you need to go back and say, well, provided that LM itself is equality comparable, then a tree of LMs is also equality comparable, because this is how you define the cases for a tree of LMs, right? Now, so any questions thus far? No. Okay, let me just see what's remaining. Okay. Now, so just like the implementations, and I realized just right now that I was going too fast with the matter of constraints being on the interfaces. We just saw a constraint that was on the type parameter of the implementation. Now we're going to see a constraint that is on the type parameter of the interface. So for something to be ordered or orderly, right? The type is required to first be equality comparable. And so that being the case, then we have this compare function that you have seen in the case splits, right? Which gives you the trio of LT, EQ, and GT. And it has right. The typing is relatively simple, and so I'm not going to get into all of that. But the thing is that you see this entire set of types, of operators need to be provided for a type to be recognized as ordered. However, these two have default implementations. So in practice, most of the time you would only implement this one, because then everything else can be defined in that terms. Let me see. Yeah, so the book goes through the matter of giving you an example for a record of albums. One thing that I haven't taught you, but you are supposed to have read on your own, is what a record is, and you would have seen that in the in previous chapter in the what is it, the data store example that you're supposed to read on your own. So this record of ours has three data members, or as some other languages call them, fields, and it has a constructor, right? Now, nothing fancy about it. What we want is to be able to sort a collection of these, but we can't do that at the moment because there is no implementation of board for albums. Now, so the way the book does it is by kind of nesting the ordering of these and providing only a compare function. Now, a bit of interesting thing here, not much really, is that the book goes on by the what is called the what is this called, the lexicographical ordering. So it compares these two, and if we have a result that says that one of them, if we have a result which says that they're not equal, then whatever it gets, it just returns. This was, this is given that we know that compare returns an ordering, which is either of LG, EQ, and GT, right? Then we can just return what we get, and so there's no much that we need to do here. So we don't need to case split at all. Now the same goes with the next level down. So if things are equal, then we perform one extra level of comparison, and we return whatever that returns. And so this is a good presentation of the fact that the nesting of compare function becomes easier by the fact that you have chosen to return just one of the three return values. Now I think we're done with this section, and if that's the case, right? Yeah. Well, now that you have the implementation of ORD, then you can also perform. Oh, that was me going for the first yawn. Right. I got bored of my own teaching. Right. Now, so yeah, that's that. And this is a good time for a joke. Jan, you came last, so you give us the first joke.
Sure thing. What's the only thing that works with something in its eye?
That works with something inside.
In its eye.
In its eye. Eyeball, no. Bullseye.
Should I
please
give you the answer? Should I spoil it? A needle.
Please. A needle, something in
Eye of the needle. When the needle works, it sews. It has to have something in its eye.
Right. Oh, that was a good one. That wasn't a joke. That was a riddle. But thank you.
Well, I would say it was a joke. I found it in the
okay.
I found it in the kids' joke book.
Right, so it was qualified.
Yeah.
Yeah. Okay.
And we laughed just now.
Well, we did because it was qualified. Because someone thought that it was qualified. Okay,
Yes, exactly.
right. Very good. Sander, we missed you for 2 sessions, so you can now pay back your missing jokes. Please provide 2. Sander? Oh, he's again having trouble. No, we can't. No, we can't hear you. Oh, something seems to be quite right.
If he messages
Okay.
me the jokes, I can deliver them.
Boo.
Well, that's one possibility. But Sandra, I think you should rather just uh, go leave the class and come back.
Have you tried turning it on and off again?
I'll try that. Yeah, I mean, I think he did try that once, but that didn't work.
Could be something with the audio drivers not matching up. He needs to
If
go
you
into
restarted
settings.
and it didn't work, then I'm out of ideas.
Right. Yeah.
Impossible to know.
Yeah.
Okay, his audio is now connected, but his muted. We can't hear you. Ah, okay. Well, fair enough. I think that so just right, Thunder, you well, you might want to do that, but I think that for the in the interest of moving forward, I think that you should also try to send your jokes to James. And oh, this is in a language that I don't speak, and I think that this is in.
He decided to put down a cable or 2.
Right. Okay. Well, fine. Now let's proceed. So right. So now that you have seen a few examples of the implementation of interfaces, let's see some of the interfaces that are already defined in Prelude. Okay. So we start with show. So show has 2 methods, to functions that you need to define. There is so a type is showable provided that it has this function defined for it, which takes an instance of that type and returns a string. And then there is this thing which I'm afraid I don't quite know how it works, because I didn't manage to find the definition of this prec thing, and how you, I mean, well, yes, I did find its definition, but unfortunately the definition was not informative enough. But the idea is that sometimes when you want to do pretty printing, you want to have you want to define precedences of your data types, precedences of your type constructors, so that you can avoid extraneous parenthesization. And so this is taking 2 parameters, because the first of them is the precedences, and the second one is an instance of the type that you are working with, and only then it gives you a string, right? Now, if someone finds out how it works, then please also let me know. I failed to find anything. Now, and you have seen the fact that print line and print, they require the type parameter of theirs to be showable, right? So that's that. Right. Now, there are also numeric interfaces. And so one thing which is very interesting, not very interesting, no, I do take it back. One thing which is which we haven't seen thus far in the book is that there are hierarchies of interfaces. You actually saw one example of that, which is EQ and ORD, but so the thing is that if everything that is ORD needs to be EQ. So there is a two-level hierarchy over there, but hierarchies can be further deep, right? So here is, for example, num, which only goes. I think James, you asked this question at the second session, that nat is so big. Do we have anything which is less constrained, or less constraining, right?
Yeah.
So yeah, here is where that is. So num provides only addition and multiplication. Neg also provides negation and subtraction and absolute values. Integral also provides operations for integer types, so like casting and all that. And there's fractional on top of that, which performs kind of division and what's that? The mod, right? So code speaks much better here. We just erase these. So here is where code speaks better. Right. So those are the ones that you get for num. In addition to those, you get this 3 for neg. Then if you want to perform some divisions, and this is what you get. And then there is the matter of performing reciprocal and division, because fractions can work out with two numbers, and you can get two on top of one another, and in particular you can get a reciprocal, which is one on top of a number. Now here is a bit of the implementations of all these all this hierarchy of interfaces in Prelude. Right. I'm afraid in this chapter, the most interesting example is this, which is sorry if it is not very exciting, but this is syntax that is quite useful. The book doesn't get deep at this level, but if we get to go further in this book, you will get to appreciate some of it. So the idea is that we would like to have a simple calculator, right, in which you can produce expressions like this, for example, which is an abstract tree for this concrete syntax, an abstract syntax for this concrete syntax, right? And you would like to be able to evaluate it, right? So this is your same expression, but you can now also evaluate it, right? Now the idea is that we would like to define that evaluator, right? Now, when we want to do that, well, the first step in TDD is that we define the types. So that's the reason why at the bottom of the page you see the data type defined. The data type has 4 type constructors. It's either a value of a type, then there is addition, there is subtraction, and there is multiplication, right? So quite simple. Come on. Right. Oh, I missed 2. There's also division and abstraction. And abstract values, not abstraction. And so evaluation of these is quite simple. You get for example, if you have an expression which you would want to evaluate, and it's an addition, then all you need to do is to recursively evaluate the left-hand side of the addition, or left operand of the addition, and sum that with the right-hand side of the addition. So it's a relatively simple thing. Now, so you perform this recursive evaluation. One thing to notice is that given the number of operators that you're using here and here, right, you need to make sure that the type of the expression, the underlying expression that you're getting is both an integral and a negational. Right, I think that is how you pronounce neg. So, right, that's that. Now, but then you see, this is writing this is cumbersome, right? You would rather want to write something like this and be able to still evaluate it. So there is some support available for that, and believe me, this is something that you would highly appreciate if you need to work with languages like C++, where this level of support is not around, right? If you have ever done a compiler in a language like C++ or in Java or in C#, then you know that this is rather a magic, that what I'm going to show you. So, now we would like to facilitate that usage of this when we want this. All right. Now the way to do that is that you would say Well, you know what? An expression of a type is itself an instance of num, provided that that underlying type is itself a num. Why? Because add can work when we want to have a class, and mul can work when we want to have. Well, maybe I should do it this way. Mul can work when we want a multiplication, right? Now, then, now here's a bit of familiar syntax to you guys as a Hascaller. So what it says that if you want to produce which you need to, by the way, produce an instance of this expression type based on an integer, the thing that you need to do is that you need to take an instance of that type first, using the from int of that type, and then you compose the result. And this is, this is the O notation of Haskell, also function composition. Then you take the result to val, which is one of the type constructors of this type, of this data type, right? So that's that, and kind of the same thing here works. For you do it likewise for neg, and it works. Right. Another interesting interface is that of cast. So you look into the typing of cast, you realize that there's this type constraint, and so if you are curious enough, you would take a look into the definition of the cast interface. All there is one function here, which takes an instance of the type from, which is this type here, and tells you how to produce an instance of a type 2, right, which is the other one up there, right? That. Okay, now, so list and maybe both being monads, it's actually interesting to define one of them in terms of the other, and that's in terms of its definition, it's actually very simple. So an empty set is a list representation for nothing. What is this called? The
singleton.
Singleton, yes, thank you. A singleton list is the list representation of a just X. Quite simple, right? So that's an implementation involving two types rather than just one type. Okay, James, would you mind giving your joke, please?
My joke or Sanders' jokes, because I have
Right, you have three now. Okay,
I now have three, so you
yes.
have to choose from.
You can provide yours first.
I went on a once in a lifetime holiday. Never again.
Right. Okay. Okay, well that makes sense. Yeah, never again. Sure.
That is a joke that
Yeah.
I took from it. Won an award, that joke, at the Edinburgh Fringe. So it is objectively a great joke.
By whom? Whose award?
It was it was one liner of the year.
Yeah,
Right.
who's the judging panel for the one-liner?
I don't know who the judging panel was that year.
I don't think there is a panel. I mean, the Edinburgh Fringe Festival, I've actually been to it 5 times.
Mhm.
It's very good. It's very good. And the judges, I think that the judges are the people.
Ah,
And so you know, not everyone pays for everything in the Fringe Festival. There you get people who just rendezvous at a particular corner of the town and do the stand-up in front of the public audience in the street. And people just gather around them and start laughing and all that. It's actually very nice. And sometimes those people participate in these
judgments.
Yes. So I don't think that there is a panel to choose.
Fair.
It's just by
panel of the
public
people.
choice. Yes. It's
Yes.
yes. But it might have changed. That's how it was when I was there. Right.
I see. Okay,
There
Sanders
are
jokes.
some good ones. I've got the list up of the winners. They are funny.
Okay.
They are funny. I've got I'm not a fan of the new pound coin, but then again, I hate all change. So I do like the one line section, but I have Sanders jokes if you're interested.
Please, yes,
Indeed.
yes, please.
I just invented a new word, plagiarism.
Okay, that's a good one.
I did like that one. And his other joke being, yesterday I saw a guy spill all his Scrabble letters on the road. I asked him, what's the word on the street? It's just ridiculous. There we go. So Sander has pulled through, even with mic issues.
Yes.
Okay. Very good one, actually. That was good. That was good. Word of street. Yeah. That was a good one. Yeah, thank you. If I had time, I would document all the jokes that are spared in this class as a part of the recordings, like as a textual documentation, as the comments underneath. But I don't have the time. But that's a great collection. So if you're teaching and you see that this is a good time to spare a joke, if you have all those handy, then you're in good wealth. So, yeah,
prepared.
That's the point. Yes, very well prepared. Yes. Now let's get back to work. So, like I said at the very beginning, one of the differences between interfaces and type classes is that Idris is not very picky about where the types are and how they are arranged, and when it's working on the interfaces and the implementations. So it takes it in particular very easy with the kinds of the types that it works with, right? Now, so for example, you have all seen these ones in Idris. Well, Pascal aside, now we're speaking about Idris. You have seen monad, you have seen applicative, and you have seen functor, right? Now, these are a bit different from the previous interfaces that we have seen, because as you can see, for example, here, f of a which means f applied to the type A is itself a type, which means that this guy f needs itself to be of type A arrow B, which is a higher kinded type, because then it's of type 2 type, right? Now, let's go see the interface. So a functor is an interface in which the type parameter of it has to be of kind type to type, right? And well, every instance of that type class, of that interface, better have this function map defined for it, which takes a function of this type, and then given an instance of f of A, it gives you an instance of f of B. And so, you know, the kind of the example that you always get with functors is lists. So a map of a function over an empty list is the empty list itself. A map of a non-empty is that you perform the function, you apply the function to the first element, and you cons that with the mapping to the next, to the rest of the list. You know, you can also do that with trees, but if you want to do that, then at some point you realize that, oh, you know, in order for this to be applicable, you need to add the constraint or pass it one level down. So here is one bit of non-triviality. A vector is a bit different because you see the type parameter of this guy has the signature type to type, right? Sorry, this is the type parameter of functor, right? Now, if you want to match that with vect, so recall that vect had the type nat to type right? So what that means is that if you want to give it this form, right, you have to provide the nat thing here. But the thing is that even though you provide it, you know, it performs no role in the definition of map, right? That's why you know, it's kind of a dummy, right? Now there's also some things about folding and foldability. One thing which I really like about Idris over Haskell is the fact that Idris is very good with providing suggestive names, right? So if you look up the documentation of fold R, or essentially the foldable interface, you get to see that it does speak about the typing in terms of in terms of the element type and the ACK as the accumulative result, you know. And that is very helpful when you want to implement instances of your foldable interface. That is very important or very helpful for me in person. I mean, sorry, for me personally. So I I always mix up the types here, and if they are like A and B, like they are in other languages, including Haskell, then I have to always think which one was what, right? Now, let's see. Right, so at some point further on in the book, right. This TDD thing, gives you, when it wants to perform the fold R and fold L. Come on, right? When you look up the the types of these holds, right? You get to see that you get informative types, right? So let me see. Here is right. So initial, for example, if this is the typing of your the required function, then you realize that initial needs to be of type nat, right? And likewise, you get to see that some length is of type string to nat, which means that you have to provide a function of the, you get to see the typing that is required of you. Now, as is expected of you. Sorry. Yeah, I think this is relatively trivial. Yeah, this is the definition of what? Of foldel. Implementation of it for list. And for trees, you read that on your own. The TDD is something that you again, the TDD is helpful with the hints that it gives you with respect to the typings available, right? But not much that I need to really take the time on for the moment. Now, here's something that I wanted to pick up on. Right. Okay. Now, let me see. Right. Okay. So this function total length is trying to work out the total length of the individual strings that it receives in the list of strings that it gets. Now, if you take a look in the typing of initial, in addition to X's, which is what you get here, and LM, which what you get nowhere. Well, which relates to the list of strings. You get another thing. Come on. Which is of type to type. Well, let me start by this. What is the difference between these two? Let me be more precise. between these two and the one above? Niels?
Like the difference between
X's
T.
and T. So X is on one side, X is on,
Yeah.
on the one hand, and T and LM on the other hand. What are the differences?
Well, X's and T have or list isn't has it's like type to type, no? Or like just list.
List is of type to type, that is correct. Of a type, sorry, type of list is type to type. That's correct.
Yeah.
Yes.
So X's and elem then are the same, since list has a type string, so therefore it's just type, no? Or
I think you have a point. I'm not sure though that you stated it. Now let me give you a hint. So where in where in here are T and LM?
I guess the T and LM comes from the definition of fold R, like the name.
Ah, very good. Very good. That's exactly it. So you see,
yeah.
Right. Very good. So X is here and you can see it. But there is more typing going on, or more type checking going on than the typing of the parameters involved, the formal parameters. Now, here is a bit of terminology that you might find useful. These types, the T and LM, are what is called phantom types. All right? They
Phantom?
show up, yes, phantom,
yeah. Phantom, yeah.
Right? Yeah. They show up in the typing or in the type checking, but they don't show up in the explicit typing of the items involved. Right? Now, so in particular, in the definition of total len, you don't see anything regarding T or LM, right? You only see X's or X's, right? Now, okay, Sander can't talk, so otherwise I would have asked him the question now. So, Jan,
Yes.
tell me which thing here is the T and which thing here is LM.
LM is the initial, since it's of a single thing, it's the accumulator. And then T is the sum length.
T is what?
If we match with, oh yeah, I'm looking at the screen card. If we match with like the folder, sum length would have to go from type to type.
Right. Well, we're seeing the.
Or am I thinking about this wrong?
No, you're not quite right. Right. The typing of sum length is that, and like I explained, these two. These two don't show up. Yes, they are phantom types, which means that they don't have any representatives.
Oh, this is the type for initial. Oh, right. Yes. Okay.
Okay, James, please.
I think that T is the type of, because for example, Foldar takes a list, for example, as an input, but it doesn't have to be a list. It could be any T which has kind type to type.
That
So
is
I
true.
think that the T is the list-like thing.
Absolutely. So
The
And
foldable,
here,
I guess, yeah.
no.
No, not the
Here
fold.
in this very instant, T is list.
Yes. And
Okay.
LM in this very instance is string, I think.
That's true.
Ah, okay.
Yes.
Okay.
And so TLM is list string.
That is true. That is very much true. Yeah. Okay. Thank you very much indeed. So yeah, that's that. Right. So right, the book at this point talks about the join operator of monads, and you guys being hardcore Haskellers, you know what that means. So I'm not going to get into the details. The other thing is that it enjoys telling you about how it comes that maybe can itself be a monad by providing a definition of the monad for maybes, right? Now, one thing which is interesting is that monad takes a type, right? Takes a type it takes a type which is of kind type to type, right? Now, for that reason, you see that this maybe thing, it's not maybe of some type, or well, maybe I should maybe of T, because if we would have provided that, then we would have already supported it with the type parameter that it takes, which means that it would have been of kind type. So that maybe is of kind type to type. Maybe of T cancels this one out. It would become of kind type rather than type to type, right? So that's one thing which is interesting. And it also tells you about pure, and it tells you, look, there is something called functor that we would see more about in the next chapters. Unfortunately, I am not going to cover those chapters in this module, but just so you know about them. And I think that pretty much is the end of our our chapter. So one thing though, let me just very quickly share with you Studio. Right, so the book does talk about the default implementation of the monadic operations. So I did a quick search to see how they are defined in terms of the one another, and you know what, I guess you guys are familiar with this definition of the two in terms of one another. I think this comes from Moji himself, so this is quite an old definition, but but this file in particular is quite interesting to look into. So you know, it has a very quick summary of how things can be defined in terms of one another. So it's very instructive if you ever make it to. If you want to see where it's defined, you know, this is the path. It's called the interfaces dot Idris. So that concludes this session of ours. Unless there are any questions that I need to take at this point. No? Okay. Now, before we go, Niels, you didn't give us your joke, so just would you mind, please?
Okay. Knock, knock.
Okay, go on. Who's knocking?
Interrupting cow.
Interrupting cow.
Who moo?
Okay.
Yeah.
Okay, well, that was you do good competing jokes. Thank you. Keep doing that. Okay. Thank you very much, everyone. See you on Friday.
Yes, indeed.
Bye.
See ya. Bye-bye.
Bye-bye.
Bye.
Cheers.
Bye.
Bye.